an amazing speaker. Please welcome Luka Kladarić.
Thank you. All right, so welcome. I'm thrilled to be here, and many thanks to the organizers for inviting me. Despite what my badge says, I am not an organizer. So welcome to The Platform is Dead, and long live the platform. If you're asking yourselves who, my name is Luka Kladarić. I'm there's a delay. I'm a chaos manager at Sakura Collective. It's a consultancy that I founded. We deal with chaos. We don't do greenfield development. We don't do features. We won't put buttons on your websites. We won't build your mobile apps. If you are drowning in tech debt, if you have performance or security issues, we'll put you on the right track and then hand off to a team that will continue the development. So I'm a recovering web developer of over 10 years. These days, I am an architecture, infrastructure, and security consultant. I'm also a startup founder and a remote work evangelist. So before we get into the actual talk, what do I mean by platform? I'll be talking about internal hosting platforms, the shared environment that all engineering teams use to host any kind of back-end application, web or otherwise. So 2 years ago, I was doing the conference circuit with a talk called Zero Downtime Data Center Failovers, with the subtitle of Switching Hosting Providers for Dummies. It was a zero downtime migration between two cloud providers, and it was about the tech stack that allowed us to execute this migration. So I'm here to update you on that deployment, and the pain that we noticed over time, and what we replaced it with. The actual contents of the talk are not that important, but I'll give you like a quick crash course in what I talked about back then. So the old stack was comprised of Ansible, Jenkins, HAproxy, nginx, and Icinga. Ansible was our config as code solution. It was our tech of choice. We used it to declaratively describe how we wanted our servers to be, to act, what we needed them to have installed, and so on. It was also abused for deploys. Jenkins was our CI/CD tool of choice. We used it to build the artifacts and then ship them using Ansible. We had a dedicated repository housing all of the jobs, so it was also config as code. There was no click interface for defining and editing the jobs. And it was great if you were familiar with it, as I was, because I contributed to it and I helped build it. But if you were someone trying to change how your application is built, it was impossibly complex to get into. We used HAproxy for load balancing. It's a software-based load balancer. And again, it was auto-configured from Ansible. So it was very powerful, very flexible. And just by defining an application in our Ansible, we would configure our HAproxy. So nobody really dealt with HAproxy directly. nginx was our application server of choice for Python applications on the application servers. It was needed to route requests to the individual applications that the requests are for. It was one more thing to keep track of. It was mostly in the way, even though it was also configured, again, from Ansible. Icinga was our primary monitoring solution. It was, again, auto-configured from Ansible, mostly out of the way, did its job with very little complaining. And it was good. It was good, It did the job. It allowed us to pull off a very complex data center/provider failover without losing any requests by building an exact replica of our existing environment at AWS. It let us grow. We added applications to it. It let us grow both vertically and horizontally. We added applications to it without any trouble, and we scaled out without any trouble. We added capacity very easily. It was simple to add additional machines because the machines that we had were defined in code, and there was nothing special about them. And we didn't need more, With a team of just a dozen engineers, it was good enough. We trucked along happily without any significant hiccups. And this went on for about a year until the first time that I went, we don't really support that. What was the request? It was Python 3. And Python 3 shouldn't be difficult. We have Python 2. but it was. We made it happen. A colleague figured out a neat trick for the same application server to run both Python 2 and Python 3, depending on just a single configuration switch. And then we got asked about Golang, and we were just stumped. This was roughly the first time that someone suggested Kubernetes as a solution, or just because everyone was using it. But yeah, I liked what we had. I didn't want to throw it out. Kubernetes seems to be an exact map of what we already had, and we were happy with it. This would just allow us to be slightly more nimble, but it would require throwing out everything that we liked. And we had no expertise with Kubernetes. There was no in-house expertise, no experience even to speak of. So the old platform really served us well. From the time when we executed the migration, we were serving about 100 requests per second at peak. We went to 2,000 requests at peak and never dropping below 400. So that's a 20x increase in the amount of traffic served with absolutely no significant changes to the architecture. We added, I think, one more load balancer. So what broke the old platform? It wasn't the Python 3. It wasn't the Golang. We figured all of those out. It was background workers. It was a perfectly reasonable request from one of the Python teams that they wanted one of their applications to have a background worker. And we didn't have anything like it, and it just took way too long, too much effort, too much time to actually support it. So we realized, it became very apparent that we reached the end of the road for this platform. And why? Why couldn't we, why couldn't we fix it? Why couldn't we improve it and grow it, evolve it? Very simple. Each thing had its own deploy pipeline all the way to the end. Because most of the complexity of each application stretched all the way to the application servers, all the way to the end of the pipeline. Every weird application had to have the entire pipeline defined. So we were maintaining a bunch of deploy pipelines in parallel, each acting differently. So what's the answer to this? The answer is containers, obviously. It's to concentrate the complexity and the complexity handling near the code base in the build stage, close to where the complexity originates, which is the code, obviously. Once you have a container image, it contains all of the complexity and all of the solutions, and then the deploy is the same. You're deploying a container. The outside world doesn't need to know about your weird application. So we also wanted developer autonomy. When we started thinking about the next iteration of our platform, we wanted the ability for each engineering team to be able to own and provision all of the infrastructure required for their applications and only come to us for advice, for help in critical situations, but for us to not be a bottleneck for them. So how do I containers? How do you even get to having containers? I spent a few days trying to cram them into our Ansible, HAproxy, Jenkins setup, and the more I looked at it, the more components I threw out and replaced with more natural fits. So what are those natural fits? We threw out Jenkins and replaced it with Travis. Jenkins is self-hosted, so that means that you have a box that you're maintaining. And that means that most of the time it's bored. It's not doing anything because most of the time developers are not shipping code. They're writing code or they're sleeping. So it's bored, over-provisioned, or another thing you need to manage scaling for. Travis is a much better fit for a high-velocity engineering team. And Travis files are slightly more readable than Jenkins files, slightly more easier to get into and understand what's going on. And building container images allows the teams to explain the complexities of their code right next to the code base and fully control how their applications are built and deployed. So, OK, we built a container image of one of the applications. What now? How do you run a container on the internet today? First, there's Kubernetes. It's been mentioned a few times today already. I mentioned it already. I'm not an expert on Kubernetes. From what I know, it's a collection of software that exists otherwise in the world but isn't actually used otherwise in the world. It makes it easy to start building massively distributed systems and very painful to maintain them in production. I dislike the kitchen sink approach where you're using Kubernetes, and that's it. That's, And from what I understand, it takes roughly the human resources of running a data center to actually run Kubernetes in production. And one of my favorite reading materials on the internet today is Kubernetes horror stories, postmortems and so on. Those are entertaining reading material. So I may be 100% wrong. Please find me after the talk. I'm happy to talk about my opinions on Kubernetes, and I would love it if someone would prove me wrong. I have not yet met a person that can do that, despite a lot of people talking about Kubernetes. So after Kubernetes, there's some other bad attempts at solving the problem. I'm not going to get into them. And then there's a whole lot of nothing. And then there's Amazon Elastic Container Service. So ECS is, in my perspective, Kubernetes. It's the same approach to the same problem, but it's built with Amazon primitives. So it's built with the same services that we already use, that we already know, and that we already love, and that we've been using for years. So the building blocks for ECS are Elastic Load Balancer, Route 53 for DNS, and so on and so on. So what is Fargate? I'm introducing a new term, Fargate. Fargate is, I haven't found a good explanation, a good one-liner explanation for it, so I'm using my words. It's serverless ECS. ECS is kind of like Kubernetes, where you say, these are my machines where I will run my containers, and then here's the containers that will run on those machines. ECS is exactly the same. Fargate is, I want to run containers. Here's a container, run 10 of them, and I don't care where they run. So you get to forget about where it's running, about cluster capacity, about room to grow, and so on. So ECS, Fargate, right? I liked the concept a lot and decided to just go for it. Initial expeditions into it were painful. The console, the web console, supporting both classic ECS and Fargate is very confusing. And there's so many things to click and enter that by the time you're done, by the time you have something running, you have forgotten the first steps. You've forgotten what you did to get there. So how do we fix that? And the answer is CloudFormation. CloudFormation is infrastructure as code, something that we actually had to admit we didn't have. With Ansible, we would provision manually the machines that we would run Ansible against, and then we would run Ansible to configure the software. But how many machines we had, which types they were, which sizes they were, we didn't have that. CloudFormation lets us declaratively describe the amount of various Amazon resources that we need. So CloudFormation lets us also deploy the same basic necessities that everything else needs. So the VPC, the subnet, the subnets, the gateways, the firewall rules, the load balancers, the DNS zones that everything else is going to tie into are all also infrastructure as code. And we use it to deploy multiple accounts that are configured exactly the same. One is for production, one is for test, one is for dev, and so on. We have the resources that then individual applications expect to find in those accounts. So you say, I'm deploying my application, and it's going to tie into the load balancer. You don't have to say this specific load balancer. You just say the load balancer that you know is going to be there. So this simple reuse means that application templates are short and very specific to the application that is being deployed. They don't have any of the there's no boilerplate in them. And before anyone asks questions about Terraform, there's a very clear reason why I'm in CloudFormation, and that is the CloudFormation console. Tying to the developer autonomy that I mentioned, it was very important for us to be able to see which resources are provisioned, why, who provisioned them, who ran which templates, and so on. And Amazon's CloudFormation lets us see exactly who deployed, when, what the changes were, and so on. So despite the horrible YAML with functions, but not really variables, but not variables or loops syntax, I still prefer CloudFormation over Terraform. Icinga, the monitoring. I like Icinga once you get to the point where you don't have to look at Icinga config files, or you have them auto-generated. I'm a fan. And CloudWatch, it's inferior in terms of frequency, configurability, resolution, but it wins on the grounds that it isn't a thing that I need to manage. It's just a thing where I define. I haven't had an outage of CloudWatch. So Icinga's out, CloudWatch is in. And also on the grounds that you can be configured through CloudFormation. HAproxy, I'm a big fan. I love HAproxy. But if we were being honest with ourselves, we weren't really using any of its advanced features. We were just using it to route requests to the applications that that were in charge of those requests. So Elastic Load Balancer can do that, and we were already using Elastic Load Balancers to balance between our HAproxies. So HAproxy is out. So at this point, some of you are like, OK, yes, I know all of these things, but how was it actually implemented? So the base networking CloudFormation stack is the stack that we deploy to each of our Amazon accounts. It includes the things that are shared between applications. So VPC, subnet, gateway, DNS zone, Elastic Load Balancer, both private and public. So you can have an application that is only internally accessible or a public application. It has the ECS cluster definition and the security groups of what they can access and so on. And this stack is deployed from GitHub by Travis to all of our Amazon accounts. So I could spin up another account with the same prerequisites in about 30 seconds. And the actual CloudFormation stack for the application, it has just the task definition, so like what actually runs, the service that defines how many things you need. Do you need 2 or 4 or 10? The listener rules for load balancers, where the logs go, stuff like that. And here's my favorite part. Everything is in one repository. You have the application code, the Docker file, you have the CloudFormation template that describes all of these things, and you have the Travis file. So Docker file explains how the application is packaged, how the container image is produced. Travis file explains the interactions between the various things. So Travis file says there's a build step that uses the Travis file, there's a push step that sends it, and so on. And it's easy to follow. Even if you're first checking out an application, it's easy to follow. You know that you look at the Travis file, you know that you look at the Docker file, and you look at the CloudFormation template. So the CI/CD flow is very simple. You have a GitHub, you have a push to GitHub. That triggers a Travis build, which produces a container image. It pushes that container image to ECR, which is Elastic Container Registry. And then you have a Travis deploy job, which runs the CloudFormation, which does the whole rollout. So what are the benefits of this setup? Like I said, all context and complexity about an app is in a single repository. Previously, this was 4 repositories. So you'd have the application code. Then you would have the definition of the deploy pipeline in the Jenkins repo. Then you would have the definition of the application in the Ansible repo, and then you would have the DNS records in the DNS repo. All of these things are now in the CloudFormation, in the one repo with CloudFormation. Introducing weird applications into this ecosystem doesn't make other applications weird. You can do a very, very weird thing and have it be completely isolated. There's no self-managed single point of failure. There's no deploy server that we manage. There's no build server. There's no managed load balancer. And if the things that we rely on start falling over, you're going to hear about a lot more important stuff being down than us. It's trivial to add new environments. You can have different branches mean, you can have a dev branch and a production branch and a test branch. You could even have pull requests go live before they're merged. So you could take a repository, edit some template, and just by creating a pull request, you get an instance of it running. And you can go and check it out and be sure that the change that you wanted to make is the one that you're seeing before you merge into the branches that other developers use. It's trivial to scale. It's practically limitless. As limitless as the cloud goes, basically. and as limitless as your code is well written. But once you have this set up, you can go from 4 to 400, like that. So what are the hurdles? What are the problems with this? CloudFormation is extremely fragile initially. Until you start to understand the places where there are significant problems, where there's not enough clarity on how things work, it's going to be it's going to be a slightly hostile environment. It takes a lot of trial and error to get to a place where you're being somewhat productive with CloudFormation. It took me weeks to get to the point where I have an idea and I know that I can execute it. First deploy failing means you have to delete the entire thing to retry. This is the most maddening thing about CloudFormation. If you create a new thing and that fails, you cannot retry. You have to log in and delete. If you have a thing that works and you change it and it fails, it'll roll back to the place where it worked and you can retry. If it fails initially, there's no retry. This is the stupidest problem I've had to solve in the last 2 years of doing anything. Elastic load balancers require that the rules that you attach to them have a priority, which is a number that is unique. So if you have a load balancer and you want 10 applications to be served by it, each with a different virtual host, as a developer, as an engineer, I don't care which order the rules are executed, because only one rule can match one request. So it doesn't matter what order they're in. But Amazon cares, and Amazon insists that you give each rule a priority. In the end, I had to write a Lambda to assign sequential numbers to my rules to be able to do this reliably, and it's the stupidest solution to the stupidest problem I've had recently. But the biggest problem, the biggest hurdle by far, and the one that has caused us to be very much behind our schedule on this project, is Dockerizing legacy applications. This would happen with any tech. It doesn't, like ECS or Kubernetes or whatever you end up doing. Figuring out how an application is actually built, pulling out the weird little complexities that are baked into your pipelines for the various different applications and localizing them and bringing them closer to the build step has proven damn near impossible. There are applications that after several weeks we still don't know how to build, which I could not imagine really happening. Beyond that, the platform is running smoothly. It's scaling as expected. It's reacting to surges in traffic without us really noticing. But the migration is painful. Questions? Nope. Sorry.
Thank you. First.
I'm offline. I'm online. So, okay, first of all, thank you for your talk. An applause. As for the questions, we have 3. The first one is, tell us about one of your K8S horror stories.
Sorry?
Chaos.
Oh.
Or Kubernetes.
Horror stories with Kubernetes. I don't really have them. I just, the ones that I read about. There was one, it was a massive American retail chain, something like Target or something like that. It wasn't Walmart, but it was Target or something like that, where they had a thing, the service discovery thing started failing, And the more they tried to fix it, the more things went down, and it took them days to recover back to full operational capacity. And it just points to the fact that Kubernetes obscures a bunch of complexity and presents a very it seems complex, but when you look at it, it's easy to understand that you do this, you do that, and you have 10 things running. But when those things, the auto-scaling, the auto-healing, auto-migrating, when those things start to fail, very few people have the understanding of what actually happens under the hood and how those mechanisms even work. So one of my favorite things is when someone talks about Kubernetes, I say, OK, here's 4 boxes that run your thing. Is what happens when I kill one? And if they know how to answer that one, I say, OK, what happens when I kill the second one? How do you even diagnose these things? How do you avoid these things? How do you recover from these things? And a lot of people talking about Kubernetes today aren't actually using Kubernetes in production. A lot of them will say they use Kubernetes, but when you say, OK, do you use it in production? Is it the thing that drives your production traffic? Most of the time, the answer is no. So that's my problem with it.
The second question, tell us about, your opinion on GitLab CI instead of GitHub's Travis.
So that's not a fair comparison because GitLab is baked into, GitLab CI is baked into GitLab, whereas Travis is not directly. It relies on one another. But also, GitHub now has actions and so on. GitHub is moving to that. My feeling on this is that GitLab is a Me Too product. Like, look at me, I have these things as well. And I've never really given it proper attention. I've always preferred GitHub over GitLab and Bitbucket and all of those. Like, there are alternatives, but I think GitHub is the one. So I don't really have direct experience with GitLab CI. I can't talk about whether it's good or not. I just primarily prefer GitHub, so I stick with GitHub tools.
And there's a second question. What do you think about AWS CDK?
AWS what?
CDK.
CDK, Cloud Development Kit. Haven't tried it. My team is it's primarily. Wait, that's the thing that's similar to Plumi, right? The CDK, no? I don't actually know.
OK.
Yeah, I haven't tried it.
OK, so we have lots of questions here for you. Were you in a situation where CloudWatch didn't log enough, so you had to extend to something else? Example, memory logging on Windows.
Yeah, I mean, CloudWatch. Turns out CloudWatch is good enough for most of the things. When you get to a situation where it's not good enough, then yes, you're gonna reach out to something like Icinga that we have, or Datadog, or there are many solutions like that. For the most part, I think it covers the things that you need for most of the things, it covers, and the things that it doesn't cover, you just reach out to a different solution. I love Datadog. They're expensive as hell, but worth it.
OK. What is the infrastructure price before and after, and for which rank or scale, number of instances?
What's the infrastructure?
Before and after, and for the which rank of scale, number of instances?
Oh, number of instances. So the old infrastructure was something like 100 boxes, of which I want to say half were application servers. And then there were some database servers that we had to manage that we couldn't use cloud databases for. And then there was a bunch of auxiliary things like LDAP, and we self-host Sentry, and when we self-host HAproxy that we kill, and so on. With the new one, it's difficult to tell because those instances are just gone. They're dead. We kill them. And the new one, you don't measure by instance, and they're auto-scaling and so on. The primary reason why we didn't really bother with comparing dollar for dollar is because with the old platform, we didn't have the flexibility to say, this application is very important. It has a lot of traffic. We need it to be running very wide. Whereas this application is literally the screen in the cafeteria that lists the lunch menu. So the lunch menu and the most critical application run with the same amount of resources. With the new stack, we can run the lunch menu on the one single box that it deserves, whereas the critical application runs 40 instances. So I think just by that difference, we're still breaking even though Fargate is clearly more expensive than rolling your own stuff. Because of that, we never bothered to even look at the direct comparison. Yeah.
And the last question. Why not simply Docker Swarm plus GitLab CI and any normal hosting?
Why not Docker Swarm? I'm going to ignore GitLab CI because I don't have experience with it. Docker, the company, does not instill confidence. They are constantly in the news as being in trouble. You don't really hear a lot of people talking about Docker Swarm or Docker products in general as a commercial thing. Docker has given us many years of DevOps and scaling fun and local development and so on. But as a commercial provider, I do not value their offering. I looked into Docker Swarm. It really didn't solve directly the problems that I wanted solved. CloudFormation with ECS solves the problems of rollbacks, solves the problem of handling deploys and rollbacks and managing scaling and so on. Docker Swarm I haven't really seen in a serverless context, which is another thing that I found appealing, where I don't want to consider the capacity. I want to consider how much we're spending, how many instances we have running, but I don't want to have a number to which we can scale. I want it to go, if I want to increase my spend by 40x right now, I want to be able to do it. I don't want to go to provision boxes that will run the 40x. So from that perspective, it didn't really make sense to even try Docker Swarm.
That's all. Thank you once again.
Thank you.